So in this video, we're going to take a look at how we can get from voltage and energy to mass calculations or mass values. So, how much of the electrode gets used up in order to generate a certain amount of energy and so forth. So to do that, we need to focus on some new terms of electricity. And so these next few slides are going to give you some of the terms and especially the units that we're interested in. You're going to want to have a list of these kind of in front of you with their equivalents so that you know how to cancel units out and so forth. First up is the volt. We've seen that before. It's the electric potential difference, the EMF, the electromotive force, between the two half cells. Unit-wise, you can see that we learned before that it was a joule per coulomb. You can also have a watt per amp, and then a watt is actually kilogram meter squared per second cubed. So you've got all of these expressions of voltage that you want to not necessarily be familiar with, because I would give you everything, but just be able to convert back and forth. Then we have a coulomb. Again, you've heard coulomb before. That's the unit of electric charge. A coulomb is equal to 6.24 times 10 to the 18 electrons. It's also equal to 1 amp second. This is actually a very important conversion that we are going to see quite often. It is also equal to 1 Faraday volt. So a Faraday, again, we hit this once before, but just to reiterate, a Faraday is the quantity of electrical charge in 1 mole of electrons. So the charge of an electron is 1.6 times 10 to the negative 19. Avogadro's number, 6.02 times 10 to the 23rd. So a Faraday is equal to 96,500. I think I gave you the 498 before, or 489. But 96,500 coulombs per mole, or joules per joules per volt mole. Good gravy. An amp is a unit of electrical current, the amount of electric charge that passes a point in an electric circuit per unit of time. So an amp is a coulomb per second, or 6.24 times 10 to the 18th electrons per second. So you can see how these things are all very related to each other. So here's an important idea. When comparing amps and coulombs, an amp is the flow rate, how many particles per time. Coulomb is the number of particles. And then finally, you've got a watt. It's a unit of electrical power. Like we said before, a watt is joules per second, or kilogram meter squared per second cubed. Usually it's this version that we're going to use it in, but note that it's also this. And so a kilowatt hour is really how the electric company charges us for energy. So that's another thing that you may see in some of your questions. So a kilowatt hour is 3.6 times 10 to the 6th joules. All right, so taking a look at some of these calculations from mass to energy and so forth, mostly it deals with the concept of electrolysis. This is a process where electrical energy is used to cause a non-spontaneous reaction. So in this case, the voltage for the cell is going to be negative, delta G is going to be positive because it's non-spontaneous. So, normally you have a battery working. You've got the electrons moving from the anode to the cathode, generating a positive voltage. But in electrolysis, you actually have to put energy in. So here, in order to get sodium and chlorine gas out of sodium chloride, it actually requires energy to do that. So this is an example of an electrolysis reaction. You've got the electrolysis of water. We're going to do this as a demo, so I'm not going to spend too much time on this. But when you do electrolysis, like I said, a lot of times you want to know how much mass is involved in order to get a required amount of current, or how much current is going to be used in order to generate a certain quantity of material and so forth. So a lot of times this is kind of the sequence of calculations that we're going to do. You're going to go from the current, or the number of amps that you've used, converting that into charge, converting that into how many electrons, and then from the number of electrons in the balanced equation, you can get to moles, and then ultimately to grams via molar mass. So remember that a coulomb is amps times time. This is the thing that's going to help us get from the current to the numbers of electrons. And also remember that 1 Faraday is equal to 96,500 coulombs. All right, so here's an example. How many grams of calcium will be produced in an electrolytic cell of molten calcium chloride if a current of 0.452 amps is passed through the cell for an hour and a half? So remember that an amp is the number of coulombs per second. So at the anode, what are we going to do? We're going to split this stuff and make it the elements from it. So Cl minus is going to go to Cl2. That's obviously a loss of electrons. The calcium is going to gain electrons. And so the overall reaction that's going to take place is this one. Okay. So, I see what we're doing. All right, so what we're going to do is, here's our amperage. Amperage is coulombs per second, so I'm just going to start off right away with coulombs per second. We're doing it over the course of an hour and a half, so times 1.5 hours, and then 3,600 seconds per hour to get rid of all the time. That gets us into a certain amount of coulombs. We know that for every 96,500 coulombs, we have 1 mole of electrons. But notice up here, there's 2 moles of electrons involved. So 2 moles of electrons per 1 mole of calcium. All the units cancel out appropriately, except for the calcium, for the quantity of calcium. So we wind up with 0.51 grams of calcium being produced over that hour and a half with that very small amperage, or that very small amount of energy change. Electrical work in terms of I don't know what. I'm at a loss here. This is all stuff that I'm not comfortable with, so forgive me if I hesitate. All right, so Gibbs free energy is the amount of useful work that can be done from a process. But remember that Gibbs free energy is also equal to negative NFE. So we can figure out the maximum amount of work possible based upon this idea. So for a galvanic cell, the delta G is negative. So it's generating energy that the battery is generating energy that we can use. In an electrolytic cell, delta G is the amount of energy that we have to put into something to get it to work. So it's the external potential that's going to be applied to the cell. Electrical work can be expressed in units of watts times time. So a joule is equal to watts seconds. And then a watt is the unit of electric power. Remember, we reviewed that earlier. And then we said the power plant uses kilowatt hours, which we said was 3.6 times 10 to the 6 joules. So, reviewing those ideas, we want to calculate the number of kilowatt hours of electricity required to produce 1 kilogram of magnesium from the electrolysis of molten magnesium chloride. If the potential is 5 volts. So, look at what we got. We've got this equation that involves, we don't really have to write the half reactions. We know that there's 2 electrons moving, and that's really all we want to worry about. So we've got the mass. We're going to convert that into moles of magnesium. And since there's 2 electrons per mole of magnesium, we can get into moles of electrons, and then we can ultimately get into coulombs. And then from coulombs, we can get into kilowatt hours this way. So again, all of this is derived from all of those equivalents that we had previously taken a look at. So how many kilowatt hours of electricity is it going to require? 11 kilowatt hours. So that lets the company know what their electric bill is going to look like at the end of the month if they can predict how much energy they're going to consume doing a particular process. Okay, we're going to get out of math and into just some battery stuff. So I think we'll stop here and do a new video for that.